Okay, how's it going? What are we working on today? I'll pull up schedule. Courses. Good. So coming up is homework 3, like next week, finishing that up. And then after that, we'll work on that next project. Should be easy, just a little bit of rocket science. Everybody says that's easy, right? Has anything come up so far on homework 3? Anything new, weird? Yeah. Nice. Yeah. So sometimes coming down. So like if I come down here and just go straight into like if I just try to run this stuff that I was working on yesterday, sometimes it's like stuff got run out of order because I haven't run like every cell and everything's a little out of order. So like this, I gotta move. If I'm gonna use Euler step, I have to define it before I use it. But then also it's telling me stuff like PLT is not defined. I don't know if that's a similar error. But if you're getting stuff like this where it's like, well, I don't have a variable named PLT, like it's probably something from the very beginning. And some of the hints are, like right now this says input 7, this one says input 43. So I had run 43 things before I did this already. So sometimes it helps to just say kernel and restart run all. And if it's not that, then maybe there is something else that we can work on, like that I can try to help with. Looks like I hit an error somewhere else. But my plot's working again. And here in the section after, we were playing around with, could we actually get bouncing to happen? Yeah, it's kind of neat. You can kind of see which one hit first whenever you see them bounce off the ground like that. Really, they should both bounce to the same height, but because numerically it looks like they're hitting the ground at different times and they have different speeds. But let me take a look and see if I can help that way. Good morning. before we were using just the word state. So we defined it and then deleted it, and it was still in source. Same thing. Good conflict there. Yeah. This is like what time is the schedule for? 1:30. 1:30. You're the one who's going? Compliments the color of their shirt. If you wear white socks, he'll shoot you in the head. It's just connected to the professional. I don't know why. That's like the dumbest thing I've heard. Oh, but you don't get owned. I don't like socks. No, anyways, I'll be professional guy. Yeah, you're crap. I don't know why. Because like, why would it? Right, you guys don't think these things are before? I'll try recreating this error that we were facing before, and it'll probably be so what we were seeing was that we were only seeing the initial condition and then everything else was zeros. So in this case, if you have a plot like this where your initial condition is right, but everything else is all zero, whatever you initialized it to, then something went wrong inside that for loop. So in here, it's trying to tell me that I'm missing an argument called state in that fall drag equation. And the reason for that, like if I come back and look at where this error is occurring, right here, why this function of lambda it's called an anonymous function. It's sort of a shortcut for making functions. It's really helpful, but it can be confusing the first couple of times you try it. So what's happening there is I defined the function as a function of y, but I didn't tell it where to put the y. So I need to say plug it in exactly in this spot. Like that's where I want that y to be. And then I get like my tennis ball falling, my tennis and lacrosse ball falling again, because it didn't hit an error on that first run through the loop. But I wanted to show, oh, state not defined. Yeah, let's get rid of this. So like if I just run that lambda, create a simple sort of thing of like lambda x is x squared, the output that I get is a function, like the object. It's the same thing as if I wrote def, like square of x, return x squared. So like def square of x, return x square. So we can see like these two things, there's really no difference between saying lambda x versus def square of x. It's just that lambda is a shortcut to say like I need to define a function and these are the inputs to that function. So it kind of takes these three lines and just turns it into one line. And it can be really helpful if you have a simple function, like you just want to square a value, or you just want to take like true false statements, or you already have a formal function like we have, where we have fall drag with a whole bunch of parameters, and we want to redefine it. So we could say like my LAX is a lambda of y, or state, we could call it state, of that fall drag of state, and then give it those inputs. So now that LAX function will take one input that is the state, and it's going to use those values for the tennis ball rather than, or sorry, the lacrosse ball rather than tennis ball. So kind of updating those parameters. Yeah, and square of 2 gives us 4 versus and the outputs are exactly the same because it's still returning same output for a given input. Cool. Anything else going on? Yeah.
Did you go back up to your plot?
This one? It's coming. Yeah, this one.
Why is it bouncing? I can't figure out why it's bouncing. Because I'm looking at.
Yeah, yours won't bounce. Yeah.
How do you get it to bounce?
Well, yesterday I was just like, as I was playing around, you know, I gotta try new things when I'm up here, you know, because all our data for the tennis ball when it hits, when we hit 0, yeah, it's coming up, it bounces back up. So I'm like, all right, well, how do I tell it to when you hit 0, like bounce off the ground? And I already know what the coefficient of restitution is, so I can take whatever velocity state that I have and just reverse it and subtract, or just take a fraction of its initial velocity. So I figured, like, all right, why not try it? Let's see how it goes. So first thing I did was say, if my height is less than or equal to 0, then take my velocity and just multiply it by a negative restitution. Because that was our restitution that we found, like 3/4, about that. And then otherwise, just take the velocity and leave it as the velocity. So then coming down here, just define these Euler steps. But what I found was, like, sometimes, right now I have like a lot of steps in there, so I was looking at higher resolution. No, still too good. Yeah, something like this. What I found was, like, sometimes I was almost like in a video game, if it glitches and you like end up on the other side of a wall and then you can't get back out of the wall, like you just keep bouncing against the wall, which is what was happening here, because my height was negative, so it kept reversing the velocity, but it was never long enough to get it up off the ground again. So it was bouncing underneath the ground, which you can see, like, kind of oscillating here. And if we make bigger steps, then you'll see it even worse. Make this like 31. Well, still not bad. Not good, but not bad, right? But like at some point, like here, it went through the ground and it's never going to get back up. So then I realized, like, all right, well then I need something to say that you're not allowed to be less than 0, like, unless the velocity puts you there in a time step. But after that time step, you don't still exist below 0. So when that's true, I said state 0, which is my height, is now going to be 0. So it stopped letting it glitch through the floor. And now, even for like not great time steps, it's at least not like getting stuck underneath the floor, because it's always going to be more than 0 after the bounce. The height is always more than 0, or at least equal to 0. But yeah, that was I was just playing around with it to see how I can make it more fun. At least for me. I don't know about everybody else, but I'm having fun. So then I can get like get the resolution smaller, make like 3001 time steps, and look at the difference between tennis ball, lacrosse ball as it bounces. Yeah, and again, they should be, like, they're both falling the same height. Like, they both have the same, like, root GH velocity when they hit the ground, but they're not coming back to the same, like, bounce height. So there's got to be something about, like, when you get close to 0, take smaller steps to resolve what that speed should be, or use a different integration method, right? Something's got to change. Something's a little off. But if you want to play around with it, you can use some of these if-else statements to like reverse your velocity, look for impact. It's nice when your impact is always like an actual value. Contact becomes a very hard problem when you have like moving things or deformable surfaces. But like a nice flat ground, that's easy. Figure that out. We could do like a sloping ground. That would be kind of cool. So it bounces down a slope. Just define a surface that is cambered, and then but we only have a what? Right now we only have y. We only have height. Yeah. Oh, you know what? But there is. At first, I was thinking they should be the same height, but I don't think their velocity would be the same, right? When they reach the ground. Yeah, I don't know. I guess the tennis ball, the tennis ball when it hits the ground should be moving a little slower because it has less mass. So drag has a bigger effect on it. So maybe it does make sense that it doesn't bounce quite as high as the lacrosse ball. Oh yeah.
Oh, that should be something. Those are important projects.
It's a 1 minute time. We got one of those. They really just crank us in. Well, they're taking the pictures for every single season. Not just weekend of Florida. Every single season. Create the wedding photos. You should please just show this movie on YouTube. It's you? In the suit? Yeah, the suit's going right to the shoulder.
I think I'm doing it now. This might be a good place to go. I guess this. Really interesting.
Okay, thanks for letting me know.
You should apply once.
That's like 2 days ago. Yeah. Basically.
Now, see how it looks local form. A lot shallower.
very respectful, all these ones are mostly food, so it gets more shoot. We usually have military policy. Oh, it is on the hard way, getting everything for a competition, but it catches the biggest fish. So like, just the people, I guess not. Oh, the 10 is just in the competition. Yeah. Like a team like whether and that's literally what there's no skill to what size fish you catch. Okay, so if you cast it in the water, you know for a fact that because you're better than someone else, yeah, fish will like that. Why is that? Because your bait is better. Yeah. Okay, so it's payable. Yeah.
No, I guess there's some skill for
You're stronger than a fish, though. If you're like 8 years old. You do it like that, you hit the people next to you. No. I caught that fish on the first cast. Yeah, every single cast. You got your outfit. I did get a beer out of it. Actually, I got a seltzer out of it. I don't know. It's just yeah. I mean, I didn't actually. Yeah. I would say
So we were just taking a look at like one of the homework problems has to do with convergence. Like what order convergence is this method? In the homework it's asking about Hewn step, but in general, when you talk about like how fast is my solution going to converge, there's some kind of plot like this. Sometimes this is a delta t, like a step size. Sometimes it's like how many nodes you have in a finite element solution, or like how many elements. Yeah, but something like you're taking a continuous function and saying, all right, it's not going to be continuous. I'm going to chop it up into these little puzzle pieces and make sure they all fit together. And so no matter what method you use, there's going to be some kind of like a way that as you keep making the puzzle pieces smaller, it gets closer and closer to one like true kind of solution, like the analytical or like known solution. So when I'm splitting this up and we look at like one data point, what is that actually representing? Like what is that thing? Like when I say error is 10 to the negative 1 when delta t is whatever 10 to the negative 2. What does that mean? Like it's trying to like, how do you read a plot is really kind of the question. Like what is this plot? And the first time you see it, the plot means nothing. So that's why I'm asking you to think about like what does it mean? You know.
In this plot, isn't it always the error is always the same difference away? What's the dotted line versus the solid line?
So the dotted line is showing you a slope of 1.
Gotcha.
So on a log plot, if the slope is 1, that means that for if you take the time step and decrease by 1/2, then your error decreased by 1/2. And yeah, same thing. So let's come back up to like so in this plot, we're looking at that same Euler integration method that we were just using for like the bouncing ball, but we're trying to model a spring and a mass, and there's no friction, there's no force to increase the speed. It's just starts off at 2 meters and then bounces back and forth between 2 and -2. So this orange line is the solution that we kind of know that based on the forces involved, it's going to start at some max displacement, go to some min, and then come back to the same exact max because we don't have any drag or viscous damping or anything in there. But with the Euler method, it starts overshooting our speed at every point. So it looks like we're adding energy to the system, like just because of the integration method. So you can take any kind of measure of error that you want, but in general, it's always going to be the same kind of log-log plot. So in this case, my error could be like 20 minus 2. So for this time step, my error is 18. And it's always like some magnitude. So 18, whether it's 18 or it's flipped or something, but just some magnitude. So right now it's 18. If I decrease the time step, so coming back here, we'll say N is 60. Oh yeah, let's do this. Make it 40 steps, like double. So right now with N of 30, I have error of 18. When I double that, now the error is much less. Now we're talking about like 8 minus 2, so it's like 6. So I doubled the number of time steps, or dt is 1/2. My error roughly went down by 1/2.
Yeah. Where are we getting -2 from?
-2.
You're saying like 20 minus 2 or.
This value here is 2. Like the amplitude is 2 meters. Yeah. Yeah. So whatever, and I could sum up like what is the average error over this whole time span, but it's extra work for not much gain. Like it would still be overall, if I decrease time step by 1, if time step is 1/2, total error decreases by 1/2, whether I choose 1 point or I choose lots of points. So when you're creating or you're kind of looking at someone's convergence plot, that's what this is telling you. It's like whether you think about it as like a single point in time or the sum of the errors over time, it's all the same thing, but it's telling you that the smaller you make those like element steps, like the time steps or the space steps, the better, the less error you have between your known solution or like some kind of like converged solution and your numerical solution. Yeah. Yeah, if it's second order, like second order would look like dt squared. Like if I take time and square it versus time, then like if the Euler method was dt squared convert, like if that was its order of convergence, then its slope would match this one. But Euler methods are all first order approximations, so they're always going to have like some error that's proportional to delta t. Step is a second order method, so we should expect second order. And yeah, if we come down, step, and then I think this Runge-Kutta 2 is the other one. There's step. Oh. Yeah, like modified Euler is kind of Euler's method, but one extra kind of half step in there. We're taking, like, rather than one slope, we end up with like calculating two slopes, both at the next time step and the current time step, and then halfway to where we think the next time step is. And by doing that, we end up with a better estimate of what the current slope is for our state, because we're always trying to figure out like what is the change in the state for a given time step. Oh, yeah, time flies. Coming up to the end of class. Okay, have a great weekend, and I'll see you back in action on Monday.